1.8 Continuity. In section 1.6, we use the laws or limits to evaluate the limit of functions. And many of the functions we were able to use direct substitutions. And those functions holds a property which is called the continuous function. Right? So in this case, in this sections, what we're gonna do is we're gonna look at what does it mean by continuity and how do we prove, right? Using the definitions, is a function is continuous on a certain interval or not. So to talk about continuity, and let's try to consider the following uh, graph of the functions. So if we look at the first graph of the functions f, notice that the function is defined everywhere except fa. So in this case, we know that f of a is undefined. But however, we know that the limit as x approaches to a of the functions, it does exist because left-hand side approach and the right-hand side approach go to what the same, approaching to the same limit value. Okay? So that's one case that we can see. And what about another case on the right-hand side? So this has become like, a piecewise defined functions now, right? And function is defined at a because f of a, we see that there is a closed circle right there, right? So it's defined and limit, but in this case, the limit as x approaches to a of the functions does not exist because the left-hand side limit and right-hand side limits are different limit value according to this graph that I'm giving to you. So the limit does not exist. Okay? So far we see two problems so far, right? Two picture, and one, the limits exist, function does not define. The other one's function is defined, but the limit does not exist. Or it could be also the case that function does not define and then limit does not exist, which is a hole right there as well. Okay. So uh, from those two, what I want to point out is in geometry, when we say continuous, right, we can, pinpoint a pencil and then start drawing from what anywhere that you want to designate it without lifting up the pencil and then continue drawing. So we call those continuous, in geometry. So as you can see right here, to draw this graph, I have to lift it up, the pencil, put a hole and then continue drawing on the other side. So in terms of like, calculus, are we going to define it is a continuous or not, right? So let's continue and try to uh, look at this couple more example, and then we can jump down to can we define the continuity. So in this case, f of a is defined, and also the limit as x approaches to a of the function also exists, right? But however, the difference, the problematic part right here is we notice that f of a, right, the functions at a is not equal to what the limits as a x approaches to a of the function, right? Those two are not equal. So um, I want to stop right here before I go into the third one, which is the limit to the continuity part. But uh, if you look at on this, the third example, if I would have put that, dots in that hole, then the function would have been continuous already, right? Because I can draw without lifting any from one end to the other end of this functions, because the hole is filled by what that dots. So that means like what all the functions define. Okay? So that sort of lead us to think about the continuous functions. So one is continuity, right? Right. One function is continuous at any point. Then what happens? The functions must define at any points a, and also the limit as x approaches to a of the function must exist. And on top of that, the function's value must be equal to also the limit value. As you can see, is continuous function. Okay? So those three criteria must meet. So, not necessarily all the times that you can talk about like the limits from both ends. Like for example, this next example, like radical functions, right? Then what happens is what the functions defined at a, and the limits only exist as x approaches a from the one hand side, right hand side, right? So sometimes like the continuity is only what on one from one side continuity. So we're going to talk about more details in this kind of cases. And then you can see that f of a is equal to what limit as x approaches to a from positive side of f of a. Okay? So it still hold the criteria, but it's only coming from what one side. So one-sided continuity. So in some of the proof that we do in an interval part, we need to use this one-sided continuity. Okay? So now you got an idea of like what is the definitions of continuity is going to be, right? And what are not continuous. So let's give us like, let me give you a few names for this because you may run into in the homework problem saying that you need to classify what type of continuity, discontinuous you're talking about. So for the first case, okay, what we call it is the if the functions exist, function does not define if there is a whole, but the limit exists, then this is called the removable discontinuity, right? So this type of discontinuity is called removable, right? Removable discontinuity. And the same thing for the other case, right? The functions, but this time the functions define, the limits exist, but however, the function value and the limit value, they are not the same. So this is also known as removable discontinuity. Okay. Now, on the other column, the first one, and clearly this is what the function is like, there is a gap between. So when the functions define or function does not define, and then if the limit, the key thing is the limit does not define, right? Limit does not exist, then we call this like, this type of functions most of the times will be the jump discontinuity, because you have a gap between like one part of the graph to the next part of the graph. So we call it the jump discontinuity. And the last part is called the infinite discontinuity, because because of the piecewise defined functions, the function may define, right? May or may not define. In this case, I'm giving to you as functions define. But however, the limit as x approaches to a of the functions, right? It is going to what? Infinity. So in that situations, we know that right away, this will become what? Infinite discontinuity. So now that we know the names of it, so on the test, I can give you scenario, and then you may be ask you to classify the type of discontinuity. So let's formally look at the definitions of a continuity. A function, a function is a continuous functions if limit as x approaches to a of the functions exists, and also the functions defined, and then the limit value and the function value, they must be equal to each other. And only if these criteria met, then we call it what? The function is continuous at that particular point A. And because if we know how to prove, right, continuous at a point, then you can talk about continuous arbitrarily everywhere on the functions, making a to be what? Any value in that interval. So that's the key idea that we're going to use to prove it later on. So once again, this definition is only one line, but when we look at this if part, limit as x approaches to a, f of x equal to f of a, and that means, three things. The limit must exist, the function must define, and the limit value and the function value must be the same. And those are the three things that we're going to use to prove, right? And then, as I pointed out on the next example, right, on the second graph of continuity, we can talk about what? One-sided continuity, continuous from the right or continuous from the left. In that case, we're not going to be talking about limit as x approaches to a anymore. We will specifically say a is approaches from right side or left side. But the key things that you need to remember is this part. Sometimes it's like, a little bit uh, confusing. So to talk about like, the endpoints on the left on an interval, like for example, this interval is from a to positive infinity, right? So in order to talk about the continuous at a, right, which is the left endpoint, we need to talk about what? The right side continuity. If the graph is something like this, right, and let's say my a is right here. So in this case, is what? Negative interval is negative infinity to a. But now to talk about the right endpoints on the interval is continuous, we need to use what? Left hand, left side continuity. So that's why you can see that right here, left side continuity and right hand side continuity, specifically using what? Plus or minus signs on the limit, right? Because we don't know on a problem, we will be proving the left endpoints must be continuous or right endpoint must be continuous, right? And we will talk about that example soon. So now let's move into the example of proving a continuous functions, right? So show that f of x is x squared minus 2x plus 1 is a continuous function. So as you can see, it doesn't really tell us continuous at, we only know the continuous continuity definitions at a particular point. But right here is asked us to prove continuous function, meaning what? Proving the continuous on the whole entire domain, right? No. So in that kind of situations, how do we deal with this? So first of all, this is a polynomial, is a quadratic. And we know the graph of the quadratic, which is what? Continuous everywhere from, the algebra and the pre-calc that we learned. We draw a lot of pictures, right? So in calculus, like, how do we deal with this? Right? How do we prove that? The only definitions that we know is what? Continuous at a point. That means the function must define at a, and limit as x approaches to a of the function must exist. And then the function's value and the limit value, they must be the same. We only know at a particular point. So to deal with for the whole entire domain, this is what I can point out, okay? This is what I can state it. I can say that, right? Remember, the domain of this is what? From negative infinity to positive infinity. That's any real number. So I can say that, before I started off this, I can say that my a will be arbitrary number. So let a, right, be all real number. Right? So meaning what? A could be any number that we want. So let a be an all real number. So by proving this, using this a as a general part, like the general point, then, we basically prove the entire domain. So first up, what do we need to show? We need to say that that's f of a defined. Remember, a is arbitrary, a real number, any number, right? But since this is a polynomial of second degree, I will be able to evaluate a squared minus 2a plus 1 by substituting it. So this value will define for any a. So we show that, a is already defined. And then the next part that we need to show is what? The limit must exist. And since limit as x approaches to a of f of x, that is basically talking about limit as x approaches to a, right, of what? The functions x squared plus minus 2x plus 1. And this is a polynomial, so the direct substitution is applicable. So that will be I should have said this, not direct substitution, because remember direct substitutions only when applicable when the function has like continuity function, continuous property. And we are trying to prove this is a continuous property, right? So therefore, if you use a direct substitution, what's going to happen is you're already assuming this is already continuous. So why are we still proving it? So what I need to do is I need to use what? A limit law instead of a continuous function. So in order to talk about that, I'm going to have to use a limit law and break it down into these situations, right? Using the limit law, limit as x approaches to a of x, and then plus limit as x approaches to a of 1. So that will give us a squared minus 2a plus 1. So the limit exists also. But lastly, the key thing that we want is, in this case now, from part 1 and part 2, I know that f of a is equal to what? Limit as x approaches to a of the functions f of x. Therefore, now I can conclude by definitions, okay? By definitions, f is continuous everywhere. So it will be continuous what? Function. Okay. Let's look at the next example, piecewise defined function. Okay. So in a piecewise defined function is given to you that x squared if the domain is less than equal to 1, and we're going to have to use the formula x if the domain is greater than 1. Now, the bad part is this. We are looking for the function is continuous or not at what? This time, particularly at 1. Right? Particularly at 1. So we already know what is my a it's going to be. My a is what? 1 particular case right here. Excuse me. So first stop, what we need to find is we need to find out is f of a, right? F of 1 defined or not. In this case, the functions, in order to evaluate at 1, then we need to use what? X squared, the formula. So that will be 1 squared, which is equal to 1. So f of a is defined, means f of 1 is defined at this case. Then the next case I need to look for is the limit as x approaches to 1 of the functions. Does it exist or not? Right? Does it exist or not? And we notice that the limit that we are looking for is in a part of both of the restricted domain. So we did so many of example in 1.6, right? So this basically tell us, we have to use what? Left-hand side and then right-hand side limit to find this out, the limit. So to talk about limit as x approaches to 1, I have to look at limit as x approaches to 1 from the right-hand side of the functions. And I have to look at the limit as x approaches to 1 from the left-hand side of the functions. So let's take care of the right-hand side. That is basically talking about limit as x approaches to 1 from the right-hand side. And from the right-hand side, we are looking at what on this restricted domain. So we are using the formula for what x. So therefore, direct substitution, by limit law, right? I will stop saying direct substitution because to be able to use the direct substitutions that the continuity property has to hold in a for the functions, but we are trying to prove the continuous. So by the limit law in this case, I know that it is what 1. And when the functions, right, limit as x approaches to 1 from the left-hand side of the functions, then we are looking at what in this restricted domain from the left-hand side. So we will be using the formula x squared. And substituting it, that will be by using the limit law, that will become what? 1 squared is equal to 1. So now I can see that left-hand side limit and right-hand side limit, they are the same. So therefore, I can say that what? Limit as x approaches to 1 of the function is equal to 1. So now from here, we can see that, the limits, the functions at 1 is the same value as limit as x approaches to 1 of the functions. So therefore, I can conclude that now by definitions, the function is continuous at 1. So it's very important that you write it properly and then logically on these. For the next example, I am not going to work on this, but I will guide you through so that you can sort of like, look at how to write it down, right? You can ask me questions during the office hour if you wanted to. How do we deal with this piece, absolute value functions? And then we want to show that it's continuous what? For every number C, that means what? On everywhere. C can be any real number. So the first thing that we need to understand about the piecewise, this absolute value function, we can rewrite it into what? A piecewise defined function. Okay. So f of x, I can say that it will be what? X if the value of x is greater than what? 0. 0 if x is equal to 0. Negative x if x is what? Less than 0. So to show that continuous every number C, that means what? My C can be what? Any real number which is greater than 0, less than 0, or even 0. So therefore, what happened is we're going to have to show that 3 cases now, right? 3 cases. The first case will be what? We can say that suppose C is greater than 0. So that means if we are looking at the piecewise absolute value functions, right? Then we will be getting what? Any C value on what? On this part of the graph, right? So that's basically using what? This portion right here, greater than 0. So in here, what we need to do is we need to show like before, is f of C defined and limit as x approaches to C, right? Of the functions does it exist. And that part is easy, right? Because we know that C, if C is greater than 0, you know which part of the functions you need to use. And then the next case we can show is what? Suppose C is less than 0. I'm not writing down, you need to complete the writing part. And when you look at the graph, we are talking about what? Here is a C value right here. So again, we need to show f of C, does it exist? Right, does it define? And then the limits as it approaches to C, does it what? Exist or not? Okay. So you have to be careful with that. In this case, well, C is a negative value. So when you writing it down, you need to write it very carefully. Okay. And then lastly, you know, suppose C is equal to 0, which is right here. So again, you need to show the functions defined as C and limit as x approaches to C, right, of the functions that exist. And remember that this time, when we talk about my C is 0, 0 is what in multiple formula of the restricted domain. So you need to use the left-hand side and right-hand side limits to find out this one right there. So that's a little bit more work. Okay. So that is a guidance that I'm giving to you to help, try to work it out for yourself, right? Now, we want to move on and then look into how to prove, right? It is continuous on a closed interval, because if you know how to prove it on a closed interval, then you can prove it, on one side closed, right? Either this one or this one is the same thing, but much easier than close on both ends, right? So let's take a look at on the process of a close on both ends. When we talk about, proving the function is continuous on a closed interval, first we need to prove it is continuous on what? An open interval, meaning what? Not including endpoints. And then we're going to have to use, right, the one-sided limit to prove, right, one continuous from one side on each endpoint. For example, we're going to have to use continuous from the right, right, continuous from the right to show that it is continuous at what? Left end points of the interval. And then we need to use continuous from the left idea to prove that the right end of the interval is continuous. So we have to do 3 steps, right? So therefore, it is much more work to do on continuous on both ends. But continuous on one side, one end is much easier. So we're going to do that also. Right? So let's take a look at on the very first example, right? Giving you the functions. And now we want to show that it's a continuous between -1 and 1. So first, what we need to, this is very important that you need to write it properly. First, what we need to do is we need to show that it is continuous with any number between -1 and 1, not including those endpoints. So to indicate that in general, what I need to say is I need to say that, so I'm proving number 1, right? Part 1. So I will say that let C be a number. C be any real number. Let's put it more precisely. On the interval of -1 and 1. A lot of times in short, in mathematical statement later on, you will see that as you go into more deeper into math classes, you will write it down. C belong to any value between 1 and -1. So in short, that's how we can write it in mathematical statements. So first, I already defined that C can be any real number between what? -1 and 1, but not including 1 and -1. Then we're going to try to prove that it is continuous on here, right? On this interval. So what do? Like before, to prove the continuous on between, first we need to show that what? F of C defined. So that is basically 1 minus square root of 1 minus C squared. Remember, C is any number between 1 and -1, so therefore C squared will never be greater than 1. Okay? A decimal number square is even a smaller decimal number. So therefore, this radical will always define, and that's my what? A specific number, right, for any specific C value. So C is functions defined. Now we're going to look at the limit. So we want to see the limit as x approaches to C of the function. And that is basically the limit as x approaches to C of 1 minus square root of 1 minus x squared. Using the limit law, right, we can say that limit as x approaches to C of 1, the constant, minus limit of the radical. We can basically talk about C of square root of 1 minus x squared. So using the limit law, we can say the limit of the radical is what? Radical of the square root of the limit of the radicand, right? So this is basically limit of a constant is a constant minus, using the limit law, this will be square root of limit as x approaches to 1, C for 1 minus limit as x approaches to C of x squared, right? Using the limit law. And don't really need to show it if you don't want it to, save on writing, but for the notes purpose, I'm gonna have to show it too. So now this help us to get what? Basically, um, I'm gonna write it differently because I might not have enough space if I continue going like this. So give me a second to rearrange it. So finally, this gives us 1 minus square root of 1 minus C squared. So from here, what we see is we see that the limits and then the functions, they are the same, right? So we know that from here, the function value is equal to limit as x approaches to C of x. So therefore, I can say that by definitions, right, f is continuous on the open interval from -1 to 1. So we proved the first part already, proving that it's open on an open interval. Now, we need to prove what? Either the left endpoint or the right endpoint, right? At this point. So showing that part 2, what we want to do is what we want to show at one endpoint. So I can sort of say, say that first part, let C be equal to -1. Right? So that means I want to prove first case is what? F of -1, does it exist or not? So does it define or not? So I can just simply substitute it into the functions 1 minus -1 squared, which is that will give us what? 0, so it will be 1. In the next case, I need to show that the limit as x approaches to -1. But remember, we are showing the left endpoint, so the continuous must become from what? The right side, because we don't have any graph on the left side anymore, so we cannot come from the left side. Right? So make sure you remember what I just pointed out. So that's important because you need to indicate that, right, from the right hand side. So this will give us, okay, so this will give us limits as x approaches to -1 from the right hand side of the functions, which is 1 minus square root of 1 minus x squared. Again, using the limit laws, right? And this time I'm going to save from writing. Let's write it down. Using the limit laws, I can basically what shows you this minus square root of limit as x approaches to 1 from the right, -1 from the right hand side of 1 minus x squared. So this is basically, 1 minus square root of 1 minus -1 square, right? According to the limit laws that we can use. And this is still 1. So this give us, same thing again. Limit as x approaches to -1 from the right-hand side of the function, that is equal to f of -1. So that tells us what it is continuous at that point. Okay? So therefore, I can say that. Let me write it down right here because I'm not going to have enough space anyway. So therefore, by definitions, right, f is continuous from right. You need to indicate that at what? C equal to -1. Right? Now, we're going to do the same process for the right end point, but this time it will be continuous from the left end, right? So to make it faster on this case, I'm going to try to, get a little bit lazy, copy and then paste it on this part. And I'm going to paste it right here. So let's move on to the right side. So this time, right, we know that we want to show at 1. So finding out the function value at 1. So which is still going to give you 1. But however, when we talk about the limits, we are looking at what? On the right endpoints. So it must be continuous from the left. So we are approaching to not -1 anymore, but to 1 from the left-hand side. Okay? So we need to change all of them to 1 from the left-hand side. So to 1 from the left-hand side. So that gives us the same value, 1. So now I can say that limit approaches to 1 from the left-hand side, right, of the function is equal to what? Function evaluating at 1. But you have to be careful. This time we are talking about what? By definitions, f is continuous from left at the point where x equal to 1. So now I show all these 3 cases that require already. Right? Continuous everything between the interval -1 and 1. Continuous from the right, right? For left endpoint -1. Continuous from the left for the right endpoint 1. So since I show all of those cases already, now I can finally conclude that, okay, the end, I can finally conclude that f is what? Continuous on closed interval -1 and 1. So it's a little bit more work to show, right, it's continuous in a closed interval on both ends. But if we look at on the next example, notice that it's continuous on everywhere from 1 to infinity. That's what we want to show. Only on what? The left endpoint 1. And notice that this rational functions 1 over 2x minus 1, the domain is anything except what? 1/2. And then the interval that we want to show is what? Not including that 1/2. So therefore, I can sort of see that is away from the vertical asymptotes. Right? So now, how do we show this? This is much easier, right? Because first, what I need to do is I need to show, right, continuous between from 1 to infinity. And then I need to show continuous at what? 1 from the right side, because this is the left end. We only need to do 2, not 3 like the previous example, right? So let's start and then quickly finish this up. I can say that let, right, C belong to any number between 1 and infinity. So now I'm using mathematical notation now. So that basically means what? C is any number between what? 1 and any real number between 1 and infinity. So from here, I can show that f of C, that is basically C squared plus 1 over 2 times C minus 1. That is my function value, function defined. Now I need to show my limit value. So limit as x approaches to C of the function. That is basically talking about limit as x approaches to what? C of x squared plus 1 over 2x minus 1. So according to the limit laws, right, I can basically show that limit as x approaches to C of x squared plus limit as x approaches to C of 1 over 2x minus 1. So if we skip the step-by-step using the limit law, then we will get what? X squared becomes C squared plus 1 over 2C minus 1, which is the same value. So that tells us f of C is equal to the limit as x approaches to C of the function. Oh, my bad, sorry. Let me change it into G because the functions that we are talking about now is using the G notations, right? My apology. So it has to be G. Otherwise, like, we will have a question mark where this F coming from. So make sure you change that, right? Make sure be careful on those little things also. It has to be logical. So finally, we can say that by definitions, right? Therefore, by definitions, G is continuous on the open interval from 1 to infinity, right? So we showed this part already, everywhere between. Now we want to show at what? 1. Right? So to show that at 1, so this is the second part, we're going to say that let C be equal to 1. So first case, we need to find out what is that's the functions defined as C. So first case, what is G of 1? That is basically 1 squared plus 1 over 2 times 1 minus 1, which is 1 plus half. That would be 3 half. Oh no, 1 plus 1, which is 2. Now we need to show that limit as x approaches to 1 of the functions. But this 1 is the left end point, right? 1 is the left end point, so it must be continuous from the right. So therefore, you need to indicate it correctly continuous from the right. On the test, if you do not indicate it correctly, that's where you're going to be lose point for this entire part. Okay, so that's a chunk of points right there. Now, we will be talking about limit as x approaches to 1 from the right-hand side of the functions, which is x squared plus 1 over 2x minus 1. Using the limit law, this is limit as x approaches to 1 from the right-hand side of x squared plus the limit as x approaches to 1 from the right-hand side of 1 over 2x minus 1, which will give us, using the limit law and then skipping a few steps, that will be 1 squared plus 1 over 2 times 1 minus 1, which is again will give us 2. So now this basically gave us, this situation, the function value and the limit value, they are the same. Therefore, right? Therefore, by definitions, G is continuous at 1. Right? Or to be more precisely, G is continuous from right side let's put it more precisely because we are using one-sided continuity definition at what? 1. It's very important that you need to indicate it correctly. Then with this 2 that we proved already, now we can say that it is continuous. So now finally, I can say that G is continuous on -1 to positive infinity, 1 is included. So now that we already look at how to prove the continuity by definitions, right? And we want to look into the theorems because to verify the function is continuous or not in later on chapters, we don't have time to prove every single functions by definitions. So we will use the theorems to verify that. Okay. But however, on the exam, what you need to be careful is read the questions very carefully. If I ask you to verify or prove the continuity by definitions, you have to, show the work like I did in the previous examples. Okay. So the theorems basically allow us to verify, a lot of functions a lot easier and faster. It's said that the functions are continuous every numbers in their domain. And what kind of function, which functions are we talking about? Polynomial, rational, root functions, trigonometric functions, right? All of those are continuous within their domains. So later on, I can just state it like, oh, this is a polynomial function, therefore it's continuous, so on and so forth. And what happened is like, the operations of, two continuous functions will still be continuous. Meaning if two functions are continuous at a certain points C, right? Then f plus g will also continuous at C. Same thing for subtractions, multiplications, and divisions, as long as g of c is not equal to 0. So the next example, what I'm going to do is I'm going to show you how to use, right, this theorems to show its continuous very quickly. So in this functions, when we look at it, I can basically let's say that, let f of x be equal to square root of 7 minus x. Therefore, right, so I can say that f is continuous at 3 because f is root functions and 3 is within the domain of this root function. Then I can say that let g of x be equal to x to the 4th plus 5x squared plus 1. So clearly g is also continuous functions, right? Or continuous at 3 because what? G is polynomial function. Therefore, right? Therefore, I can so I can say that now let h of x be equal to what? F of x divided by g of x. So h is also what? Continuous at 3 by theorem. Right? By theorem. And then clearly, g of x is not equal to 0, right? So I can say that g of x is not equal to g of 3 is not equal to 0. Right? Make sure you state it very detailed so that I will have no way of taking out points on the test. And I can say that n g of 3 is not equal to 0 because you can mentally compute that quickly. Right? So this is how you can, like, very quickly verify it is continuous or not, right? Using the theorems. Again, be careful with on the exam because I will ask you and show by definitions, right? Show the continuity by definitions for sure. And the next theorem is basically helping us to use the composition function because you saw that one of the theorems that take care of algebra of the functions, now the compositions of the function. If g is continuous at c and f is continuous at g of c, right, the output of the continuous function, then the composition function g of f of g of f of g is also continuous at c. So you can see that this is basically showing that the limits law, right? Using the limit laws, we can say that the limit and the function values are the same. So to prove this kind of situations, like I can see that the first example as let g of x be equal to x minus 1. So we know that, right? So that's right. G of g is continuous at 2, right? Because g is a polynomial functions. And then I can say that let right f of x be equal to square root of x. So that basically show us anything that is greater than g output will be always like what, greater than 1, right? So you can say that g of x is greater than let me just point this out because we only want to show that it's at 2 only. So g of 2 is equal to 1, right? So that is within the domain of f, right? G of 2 is within the domain of f that we're defining right here. So since with domain of what, 0 to positive infinity. So, and we also see that g of 2 is 1, which is within the domain of what, the f functions, right? So therefore, according to the definitions, f is continuous at g of 2. And now let h of x be equal to what? F compose g of x. So we have taking care of g function is continuous and f function is also continuous, right? Because g of 2 is in there at 2. So when I say that h is f composed of g, then by theorems, h is also continuous at 2, right? It's basically rewriting it. So similar things, you can rewrite it. All of them is right here. Okay. So I'm gonna write it slightly different and then more a better format than working out one by one. So this time I will say that let f of x be equal to cube root of x. and g of x be equal to x squared plus 2, and h of x be equal to f composed g of x. See that, notice I define everything in the beginning. Then we can talk about each case, right? And so we know that g is polynomial function, so continuous at 5, right? And f is a root functions, so it's also continuous at let's put it this way so that it will help you to see better. Polynomial is continuous from negative infinity to positive infinity, right? And root function, this is the cube root, so it's also continuous from positive infinity to negative infinity. What that tells you is, right, that tells you is that includes also g at 5, right? So therefore, f is also continuous at g of 5, right? G of 5 is just like a real number output, and that real number is a part of the domains of all the f functions. So by definitions, or by theorem, I should say, right? H of x, which is f composed g of x, which is cube root of x squared plus 2, is continuous at 5. And that's how we can use the theorem to, finish it up quickly with all the explanations in there. And the last part of this section is the intermediate value theorem. The intermediate value theorem is a conditional statement, if then, okay, if and then statements. I purposely write it this way so that you can see which are the conditions that we need to meet and then which is the conclusion that we can use. So usually these kind of theorems, like, the way that I try to remember is like using graphical, memorizing with the graphical approach, right? So first, what happened is like we need to know f is continuous on a certain interval a and b, okay? F is continuous on a certain interval a and b. So that's the first criteria that we need to remember, and make sure you precisely, state it as a continuous on some of the theorem is open interval, some of the theorems is closed interval. In this case, it's like what? Closed interval. So very be careful with to be specific. Okay, continuous on a closed interval. Let me use a highlight with different color. So continuous on a closed interval, AB. So that's the first criteria that we need. And then, okay, and then we will say that there is a number m, okay, there is a number m such that that value m, right, that value m is between the function value of two endpoints, which is f of a and f of b. That's the second criteria that we need to have. So there is an m, let's say there is an m, right, that is between what? F of a and f of b. So that is the second criteria that we need to meet. Now, if these two criteria are met, then what basically it tells you is this now. There will be a number c, right? There will be at least one number c such that the value c, right, is f of, when you evaluate it, that will be f of m. So we are looking at what? there will be a value C between A and B, at least one, depending on where you are talking about, where's your M is talking about. In this case, what we have, what, two of them. See that? So that's why in the theorem, it said that what, there is at least one number C in between closed interval A and B such that f of C is equal to what, M. That is our conclusion part. So this intermediate value theorems, like, later on, we will use mostly on, like, in the sum of the proof of, okay, sum of the proof. One of the things that we can look at quickly right now is this, finding the solutions, right? Finding solutions. But we don't know, is there, we are not looking for a precise one. We are just like trying to show that there is at least one solution. So in this case, what I can do is I'm going to try to put all of these conditions right here. Right? So I can say that let f of x be equal to x to the fourth minus x minus 1. So therefore, I can rewrite this left-hand side of equations to be a function, so that I can start talking about all the criteria in the theorems. Right? So the first one that I need to show is, like, is it continuous or not? Yes. So I can say that f is polynomial, right? Functions. So it is continuous on what, the entire domain, which in this case we only needed what, in a closed interval, -1 and 1, something that we want to show, right? And then the second part that I need to show is what, there is a number, right, m, such that that value m is between f of a and b, which is, this is my a and b right here. But in this case, what are we trying to show? What is our m value? What is our m that we are talking about? And notice that in the equations, if you write the left-hand side to be function, f of x is equal to what? 0. So the m that we want to show is what? Which x value is going to make it 0, right? That's mean the solution. So our m is what? Looking at 0, right? So in this case, let m be equal to what? 0. Whenever because we want to show that there is a solutions of this equation, right? So that means when we say solution, that means what? The function value is 0, which x value is going to make it 0. So we want to show that there is a solution that exists, at least one solution exists. So I would say that let m be equal to 0. And then we're going to try to find out what is f of the m point, f of -1. What is the value of f of 1? So in this case, that is basically talking about -1 to the fourth power minus -1 minus 1, which will give you negative what? 1, the value. When I substitute 1 into 1 to the fourth power minus 1 minus 1, oh, my bad, sorry, this is positive 1. And this will give me what? A -1. And you can clearly see that the value of m is between these two, right? What is m? M is basically what? That implies the function value equal to 0, which is our solution, okay? So now, this help us, right, to meet the second criteria, which is tell us what? F of 1 is smaller than or equal to m, and then less than or equal to what? F of -1. So we show that already, right? This m value is between those two. Meeting these two criteria, now I can state that, right, by intermediate value theorems, IVT, there exists, we don't know the solutions, but we know the existency. That's what we are trying to show. And that's why I say that show at least one solutions. So there, what we can do is we can say that there exists, right, at least one solutions, right? Or no, I should say that there exists at least one C such that f of C is equal to 0, which is the value of M that we are talking about, which is what? The solutions. So that means, right, there exists, that means x to the fourth minus x minus 1 equal to 0, the equations, that means, right, the equations has what? At least one solution. And this will be the, using the IVD to show, existence of the solution in this problem. And that concludes this sections.